Welcome back, and we are now recording. And of course, we have a critical problem in this class, is you're going to get hangry because you're here from 5:30 to 7:50. So please plan accordingly. Eat ahead of time. Eat during, I guess. Eat after. But after doesn't solve our problem, so eat ahead of time or during, I guess. Or run out and eat something. By the way, if I started in the future at 7:10, and would you rather have a little more time in between so you could be less hangry, or would you rather just get going and deal with it? Why does everyone say that? Why did I know the moment I asked you that you're going to say, just get this thing over with, it's Thursday night, that's when the parties begin? It's life on campus. Okay, fantastic. This is discussion. It's just going to be about the projects. Lectures are about the conceptual material. You could call it, like, for example, if you go on Amazon and look at our book, it says it's operating systems theory. Now, theory is a funny term. It's a very practical field. When we think of CS theory, we think of algorithms and complexity theory and all this heady stuff that sounds like math and is hard. Operating systems theory is just conceptual. What are the key ideas, like about virtualization, about concurrency, about persistence that are needed? And that's what we'll be talking about, of course, in lecture. In discussion, we're just going to get hands-on, look at the projects, and talk about them, and look at some code together. So as to give you a start. And of course, in the earlier projects, we do a little more of that, and as the time goes on, perhaps a little less. I will record these too, though, so you can review them if you need to. Okay, so that's discussion. Let us look at the first project. It is called, as I said, P1A. As I said, that's going to lead to P1B. The project description, I've been just lately putting them on GitHub. This is a new project. I try to have as many new projects as we can each year. Otherwise, people use this thing called asking their friend who took it last semester what they did, and therefore having a head start on the projects. So here's a new project. This project is called a key value storage system. There are some famous key value storage systems that are used all the time in industry. RocksDB from Facebook, LevelDB from Google. How many people have heard of any of these systems? A few of you, not many. Key value storage system is like a really simple, intends to be high performance database. So the idea is basically you put a key and a value in it, and later you can ask for the key and then get the value back. Yeah, there's a question. Oh my gosh, you can't read this. Is that what you're saying? Yeah, it's not readable at all. It's terrible. Now is it readable? All right. Thank you. By the way, if you can't hear me, you can't read what I'm pointing to, if you don't like what I'm wearing, whatever, just raise your hand. Just say something about it. I'll address it. So we're going to build a really simple key value storage system. Key value storage system is like a really simplified database. So there's a whole class about databases. You can take that, but in this class, we just kind of build a database. It's a first warm-up project. Of course, it's a simpler database than what you learn about in a full-fledged, SQL-compliant database. So this is a really easy thing. It's a warm-up project because it just gets you remembering how to do some basic stuff in C. This is how you're going to run the program. It's going to be called KV. And when you can, for example, put a key into it and with an associated value. So when on the command line you say P, 10, remz, it's saying put the value remz with the key 10. The keys are integers, the values are just arbitrary strings. And so then later what you can do is, for example, you can get the key 10 and it'll give you back the key and value pair that you put into the database. Now it's called a persistent key value store because, as you may notice, when you run the program again and again, the database is being kept somewhere. So in a file somewhere, this is going to give some flexibility here. It's going to store that information, and then when you run the program again to do some lookups on this database, it will access that information and then give you the results. So our basic functions are put and get, which you can think of just like a data structure, right? Like reading from something from a data structure or putting something into a data structure. It's just that we're keeping it around. It's called a persistent data structure. That's the basic idea. Any quick questions about that? Yeah?
So for the put, do we allow, we never allow the
That's right. Great question. So if you put like the key 10 with Ramsey, and then later you put the key 10 again with a different, it's a little bit centered on theme all the time, Ramsey. So if you put someone like key 10 and then somebody else's name, like when you do it again, you should only get the result of the latest put. So you don't have to keep multiple values around, just keep the latest value around. It's just like a basic data structure, right? Just you put something in it, you can get something out. If you overwrite, you can overwrite it then later. Yeah? Do you need to do like a hash table? Is that what you're asking? So internally, you will have some data structure, and that is up to you. You can do whatever you want. Now, for the first part of this project, which is going to be due a week from Monday, remember it starts bad and it gets worse. So a week from Monday, and that's, by the way, once it is an assignment, doesn't it feel like you're back in school again? Like that's when you know you're in school. Like if we're just talking, oh, this is fun, I get to see people, assignment due, school. So due a week from Monday. That's just going to be correctness, right? We'll give you some tests, and in this class, we will at some point soonish provide you all the tests we're going to use. Now, of course, you should write your own tests to see if it works. But we will provide a test, and you are graded on those tests. That's how the class works. You're like, I wrote a lot of code. Does it pass in the test? No. Your grade is then a 0. It's a very sad point for all of us. We're going to try to help you not get zeros, but we are graded on functionality. Does it work here? 1 second on the question. So that's going to be the first part. The following week, if you're enterprising, we'll have another project out, which will be Project 1B. And Project 1B will be getting inside of the operating system. So we have 2 flavors of projects. These are the outside, using the operating system services, writing a C program that uses the OS to do stuff. It's called systems programming. Most of you will, if you work in systems, you will definitely do some systems programming. And then for the 1B or 2B, those will be inside an operating system. Now, that operating system is called XV6. And we'll learn more about that at the next discussion. You don't have to know anything about it right now, but it's basically not a toy. It's a small, real operating system. It was developed at MIT. We use it for projects in here. It's pretty cool because it's like, just so many thousand lines of code that you can kind of understand parts of it to do projects that are going to be pretty cool, like build a scheduler or build your own thread library or modify the virtual memory manager or make a new file system. We're going to do all those things inside of XV6, so we don't have to worry about that right now. Now you might ask, why don't we do that in Linux? Linux is a beast. So, being able to read Linux code, Linux is written by very professional people who write very efficient C code. It's huge. It's thousands and thousands and thousands of lines of code, millions of lines of code. So we're not going to do that in this class. But at the end of this class, if you ever get stuck working on Linux or get the opportunity to, you'll have a much better conceptual understanding of all the things that are happening inside of it. Anyway, question?
Yeah, so you're going to release all the tests, right? So it's like we pass all the tests you release, we get full score on.
You pass all the tests, you get 100, you tell your friends about it, it's exciting. Yes. There's no hidden test. There's no trick. Why do I do this? I want you to succeed. Isn't that generous of me? I want you to succeed. You're going to pass the test. You're going to get 100. You're going to tell people you know about it. You're going to tell your family, I passed all the tests. It's going to be fantastic. Anyway, I feel like it's weird. I'm telling jokes, but you can't see my face. Like my face is indicating that I'm telling jokes. Anyway, that's the world we live in. Okay, back to our key value store. So, as basic idea clear? Now there are actually a bunch of commands you're going to support. They're all in the command line. So put a key in a value, key's an integer, value is just some arbitrary string. Get a key gives back the key, comma, the value, and a new line character, \n. And by the way, if you get it like kind of right, like you put the value key and the value in an extra space in a \n, you're going to fail that test. That's why we give you the test. So you work out all those kinks and you pass the test. Again, we want you to pass the test. A few other commands that are pretty common in these kinds of systems. We have a delete. So you delete in a key, then it should remove it from the database. Clear just gets rid of it, essentially mass delete. So it deletes all the keys and values. and then all just dumps out the keys and values. That's mostly for your debugging, so you can kind of see them all. It's hard to test. Well, you can test it, but you have to sort the data first usually. Okay, here's some details. Okay, any quick questions about that? Put, get, delete, clear, and dump all. Simple. It's a persistent key value store. What does that mean? That means across invocations of this program, you have to be able to find the data. Normally when you run a program, you put a bunch of stuff in memory, then the program exits, all that stuff's gone. That should make sense to you, right? The program runs, there's stuff in memory, like a hash table or a linked list. You could use a linked list in this project if you want. It's not efficient, but it'll work fine. But when the program exits, that linked list doesn't exist anymore. That hash table doesn't exist anymore. So how do we make this, the data persist across invocations, across running of the runnings of this program? And we're going to do that by explicitly storing those keys and values in a file or in a set of files. Like for example, LevelDB. Google was one of the earlier creators of one of these key value stores, this thing called LevelDB. In fact, two of the most famous engineers at Google, Jeff Dean and Sanjay Gangawat, they wrote huge amounts of the Google infrastructure. They're so prolific of engineers at Google, they kind of created a new engineering level just for them, like level 11, right? They're just known for being like fantastic programmers. They sat down and they wrote LevelDB. This is very complex. I mean, it's very beautifully written, but it's a complex key value storage system. It's built on this data structure called the log structured merge tree. It stores data in all these different files in all these complex formats, and it does that so it can be really efficient and high performance. So you can read about that. You don't have to do that. You don't have to be quite as good as Dean and Gangawat, but you can just have, you're going to have to do some kind of persistence. So here's a simple idea, for example. Let's say you have a file. So we're going to store a file in the file system. Let's say we call it database.txt. You can call it whatever you want. Let's say you call it that. So what you're going to do in your program when you put keys into the database is you're going to basically just store them in that file. So you have to open a file, you have to write some stuff to it, and then later when you run the program again, you have to open that file and then recover that information. So that's all you're going to do in this, is like create a little database file and store the information in there. Now you can again, when we do like beyond the functionality tests, in the second week, which I was getting to, but then I kind of got off track. The second week, if you want, we'll have this performance competition. And then you might want to do like a very high performance implementation of this database. That's up to you if you're enterprising. What do you get for doing like these contests? The winner will be famous. And maybe you get like a t-shirt or something. I don't know what the prize is. The prize will be very minimal. This is a public school. You're like, what about me? I'm out of state, still a public school. There's a question in the back.
Can we get the O-Step merch?
O-Step merch, absolutely. How about like a shower curtain? There's an O-Step shower curtain. No one has ever purchased one. Honestly, somebody asked for like, a t-shirt, and I'm like, sure. Then like my daughter made this kind of stylized version of the cover, and then you like go to some website and they're like, you can have all this merch, a mug, a t-shirt, they just printed a bath mat. I mean, who doesn't want an O-Step bath mat? Answer, everybody doesn't want that. So sure, we'll do some merch. I don't know, we'll have some price limit on that, but yeah, that can be something like that. So we'll announce the contest later. I would say mostly don't worry about it for now, just get a working version, turn that in, pass all the tests, get 100, call people, tell them about it. Then worry about, if you have time and energy, doing a high performance version. Don't do a high performance version first, it's just more work. Yeah? Hi. Yeah. Yeah. Oh, fantastic question. It's an advanced question. The question is, hey, what if the program dies? Like, if the program gets killed, how do I manage that database? We're not going to worry about it here. Just assume the program exits normally and you have time to save the database. A real database, which is why you're asking this question, is worried about not only saving the data when things go well, but if you crash while things are happening, like somebody kills your process while it's running, it still has to put the database in some reasonable format. That's a much harder project. We're not doing that here. I mean, you can do that. That's fantastic. Congratulations, but you won't pass any more tests. The test is just normal operation. Great question. I should write that in this description. Yeah.
So for the persistent, is it fine if I use a different approach than saying everything just one file?
Yeah, so the question is, for the persistence part, can I use like more than one file? In fact, like LevelDB, for example, that I was talking about from the famous Google engineers, that uses many, many, many files across many levels. That's why it's called LevelDB. And they're organized there, each one's a sorted, SS table, blah, 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 lots of detail there. So sure, but I would also start by doing easy version. Just do an easy version, make it work, pass the test, and then you can play around with it, have fun. Maybe do one that's going to be really good for a contest. Yes?
I think when they get stuck while doing that,
Yeah.
and you probably Google it.
Yeah.
So when a lot of us keep doing the same thing, we probably end up with similar solutions or similar.
Yes.
So how exactly is it that?
Sure. Great. So the question is, hey, I'm doing this project, I get stuck. I type something into Google, I get an answer. I then use that answer for my solution. Are you going to call me a cheater? Answer is no. Because the help you're going to find on Google is not going to help you write specific code here. What's going to get you in trouble is when you're like, hey, the project's due in an hour, I haven't started it. You might have to look at yours, I won't copy it. That's what I call an invitation to doing your own thing. Don't do that, you'll be fine. It's really, just write your own code. What is the point of any of this? To write your own code. You know what happens when you leave here? You write your own code. Is it fine to look stuff up? Sure. Look stuff up, as much stuff as you want, no problem. But just write your own code, no problem. I have never had a situation where, I'm very sure of this, where like every time someone's done something funny, I talk to them about it, and they're like, yeah, I did something funny. So there's only one case, I will remember this forever too. Somebody came in, and I'm like, look, it looks like you copied. They're like, oh my gosh, I'm so sorry. I'll never do it again. And I was like, fine. And like, gave him the 0, but we didn't make a big deal of it. Just what? I'm a bleeding heart. I'm sorry. I didn't want to make a big deal. We were supposed to go to the dean or whatever and make a big deal about it. Okay. Then 2 weeks later, next project's due. Someone else comes to me, and they're talking about this person. They're like, hey, this person works at the same company that I do, and they just sent this email. The email was, it's really hard to cheat in this class. I need help. I just need someone to write an original piece of code for me to complete this project. So the reality is you can't have some other person write all your code, but like you can't eventually that doesn't work, right? Like eventually at your job, someone will figure out you're not writing the code. So just write the code. It's fun. If you don't like it, it's a wrong major. Sorry, is there a question? Okay, good. No questions. All right, so you can do what you want. This is just a simple approach. Just have a file, store some stuff in it. There's some things down here, and then we'll get into some code snippets. So assumptions and errors, like a bad command. If you don't give a command that's proper, you should just print an error message, bad command, and keep processing. Don't exit. If you have an unexpected error, you have to kind of gracefully exit, print out an error message, exit, save your database. But that shouldn't happen, so we're not really going to test that. Like for example, when you call malloc to allocate memory, like let's say you stored your keys and values in memory in a linked list. They're certainly possible, no problem. You can do that for this project. But when you are allocating a node of the linked list, you call malloc. When you call malloc, well, you have to, that might fail. You have to check the return code. All good C programmers check return codes. All good C programmers check return codes. When you come to office hours or go on Piazza or whatever and your code doesn't check return codes, you lose credibility. Don't do that. Check your return codes. You just have to say something simple like assert that malloc didn't fail. So, but if that happens in this project, it's unexpected. You don't have to do anything fancy. Okay. The rest of this is pretty simple. These are just routines that you can use. You can, of course, use anything else that you want, but we'll just talk about a few of these examples right now. Okay, so any quick questions? And then we'll just go into some code examples. All right. Oh, yeah, in the back. I always get worried about questions from the back. I don't know why.
So the keys are integers. Is there any bounds to that?
Yeah, the keys are integers, and they will just be, they'll fit in like a 32-bit integer. So we won't like do something crazy. We have to store arbitrarily long integers. Now the string, the values they're just an arbitrary string of some arbitrary length. So that can be long. Good question. Like I said, I always get worried about questions from the back, but that one was okay. Okay. Fantastic. So let's look at some code. Not there. Here. So I'm going to do two things here. I guess I'll put that on here. Let's do two things. One, we'll quickly just do a couple C things, and then two, we'll look at some relevant code. I guess it's all relevant, but specifically relevant. So let's do the C piece first. Let's just create a new program. What should we call it? C.C. That's a terrible name. That's not what I want. Okay. Okay, let's remember can you read that? Is that big enough, or should I make it bigger? A little bigger. Okay, fine. I was getting bossed around by these students. It's my life. It's fun. As faculty, you get bossed around by students, and then as the chair of the department, you also get bossed around by all your faculty. So I'm getting bossed around all the time. But it's okay. I accept it. My wife always tells me this. It's by choice. You're choosing to be here. I like being here. Actually, 100% best part of being at a university is working with students. I'm not just appealing to you. That's actually true. So thank you for that. So anyway, let's get back into this program. This is a C program. What does it do? Nothing. It has an integer return code. That return code, and you can see returns 0. You can actually look at that from the command line, which is useful sometimes to see what program ran successfully. We'll talk about that later when we talk about how shells work. It's usually passed some arguments, argc and argv, right? But we're going to just review a couple things that you have to remember to understand that you 100%, most of the problems you'll have when you're writing programs here are going to be C-related problems. Like, you'll understand kind of what you need to do, but you'll be clumsily doing it in C and having crashes and bugs and frustration and throwing things, hitting the computer. All those things happen because you're misunderstanding something about C. So for C, you really have to understand a couple things, and I'm just going to write them down here. We have to understand memory and pointers. And I think today we'll talk a little bit how we have to make sure we understand function calls. If you understand those two things, you're like, and you really understand them, have a good model in your head, you'll be in good shape. If you don't, what happens is you start doing this, and maybe you've done this. So you've written some C programs in 354, correct? And some of you say yes, others say no, I didn't. By the way, this is the funniest thing. There's like what gets taught in the class, and then what students claim gets taught in the class. And those two things often aren't that overlapping. So I don't know why that happens, but it's a funny thing. So yes, you've written some C programs. And then what happens is when it doesn't work, you start doing things like, throw some stars in there. Boom, star. Boom, another star. Oh, ampersand. How about a semicolon? I think it's going to work. Don't do that. That means you don't understand what you're doing. The solution to your bugs is not asterisk throwing. Do not do that. It's not a good technique. Have a good model. What is the model that we should have? Well, let's look at it. So we have variables like int x. Int x is declared on the stack. So when we think about x, we have our address space, and this is our tiny address space. I'll write it here, sorry. Here's our stack. Our stack is at the high addresses. It grows backwards. Why does it grow backwards, by the way? Well, we want to have two growing things in a linear address space, so they grow in different directions so they can kind of have some flexibility and fit in there. It doesn't really matter, but it's kind of how we've done it for a long time. The heap, remember this is where malloc stuff goes. This is automatic stuff. These grow in different directions. So when we say this, is this big enough? I didn't ask. You said a little bigger, I went with it. When we say this, that means somewhere down here, there's an address, there's 4 bytes that are allocated when we enter into main, which is when the program starts. There's space for that on the stack. So that's great. We can have another type of variable. This is allocating a pointer to an integer on the stack is no different. It just makes some room on the stack for a pointer. A pointer is just an address. So that means the things stored in that location are addresses, but it's essentially no different. It's just making some space on the stack for something. One thing we call x, the other thing we're calling p. It just has that's, you can think of it like, it's a little bit confusing sometimes that it looks like that star's over by p, but you can really think of it as like, there's p and it's of type int star, right? And of course you shouldn't write your code like this because it makes you look like you're a weird. So don't do that. But that's how to think of it. It's an int star that you've declared on the stack. So again, if you look at our program over here, it's somewhere on here, there's probably very near where x is, there's p. There's room. When we entered main, there's room for that thing. So that's our first model. When we enter into a function, some room has been allocated on this stack frame, in this case the stack frame of main, for x and for p. And when we refer to them, of course we refer to them by name, but the computer the compiler turns that into addresses and just refers to them by number. Address this, address that. That's our first thing, our model. When we enter a function, we have space for the stuff allocated on the stack. Of course, we have to think a little bit about like how this is going to work. We can, of course, assign x to things. No one would ever get confused by this. X equals not 3, but 4. Now, this is weird code. Sorry, these are really dumb examples. So you wouldn't write x equals 3 and then immediately say, you know what, I really wanted x to be 4. Like, that's not what you would do. But let's say we did that. All that's going to do, of course, is whatever that location on the stack is that we call x, is going to update it to the value 4. Right? So it's going to store the value 4 to that address. Similarly, when we say p equals something, it's just going to update that location on the stack, which we call p, but again, it's just some address in our stack. Now, because p is of type int star, it would be natural to put some kind of address here. Some different addresses that are possible, for example, null, which in C is just 0, but it's also null, which means this doesn't point to anything. Or you might say it's going to point to something, and in this case it might point to the address of x. So now we have two stack allocated variables, x and p. X has some address, p has its own address, and then inside of p, inside of that container which we call p, we have the address of x. That's the basics of pointers, simple as that. And what that allows us to do, of course, is it allows us to refer indirectly to things. So for example, we can change x to 4 like this, or we could do something called dereference p to change the value of x. So for example, if we say star p equals 4, that's called a dereference. And what we're saying at that point is, don't set p to 4, say what p points to 4. And because we know p has the address of x in it, afterwards when we print here the value of x, first of all, the compiler will say, why are you doing this? This is a strange program that's really boring. But other than that, it'll say, it'll print the value 4. Okay, so that all seems, it's actually not that complicated. Pointers, everyone's like, oh, C, pointers, they're terrible, I hate them. Hate you, C. How many people hate C? By the way, that's an auto-fail in this course. So you should never raise your hand to that question. That's a really bad move. I took a picture of that. It's 100%. You still hate it. No, question. No, you're like, I don't hate it. Question. No. I love it. What's the question? Oh, yeah, great question. Yeah, I always compile with warnings all like that, so you see everything that you, like, if there's any warning, C compilers are like, so different languages have different things that it means if you compile the program, okay? So with C it means, yeah, this might work. Probably won't. You'll probably crash because you don't know what you're doing with the pointer. So a successful compilation doesn't mean that much. But warnings all gives us the ability to say, like, hey, if you think anything's a problem, please tell me about it. So you should have a clean warnings all compiled. And if you don't, you probably won't pass the first test, and therefore you won't pass the rest of the tests. So if you're getting warnings, pay attention to them. By the way, we'll talk a lot about this during this semester. When you write a program, it generates a bunch of warnings. The way to deal with that is just look at the top, look at the first one, and try to figure out why it's doing that. Don't worry about the 1,000 things that it says, because it gets confused. Look at the first thing that it says, try to figure it out, put it in Google, ask your friends, call your parents, whatever technique you want to use, all good. Look at the first thing, pay attention, fix it, and go from there. Okay, so compile with wall or -w all. So anyway, that's a very simple example of pointers, right? How we can update x directly or indirectly through p by dereferencing it. That's by saying don't, and of course on the left-hand side it's saying update p. We could of course say p equals, like we did in that code earlier, p equals p plus 1. That'll, instead of printing out 4 afterwards, it'll print out 5 because it'll dereference p here, which will give us 4, it'll add 1 to it, and then it'll say store that back in here, so it'll store that back into here and give us 5. I won't run that because it's just going to work. Now, so that's just the most basic thing. And we have some stuff like that in a C program. Now, the one thing I want you to understand about function calls, let's do a function call here. Let's call increment. And what this function is supposed to do is it's supposed to increment the value. So let's not do this anymore. Let's do this. Let's get rid of this. Let's print out that. Let's call increment x. Okay. What is this program going to print out? 4. Why is it going to print out 4? Let's get rid of this. Oh my gosh, what a strange program. Four, correct. Why does it print out 4? Yeah.
Never save the value to x. You only save it to a copy.
Yeah, perfect. It has to. Exactly. So when we call a function, we're passing these values, we're making copies of these things on the stack. So let's think about how that looks. How does that look? We have int x here. It's equal to 4. And we call increment x. And remember, the function increment looks like this. It says int value. I did that same thing. Let's call it v. And it says v equals v plus 1. But the way to think about that, we have to really think about our stack. So when we call into increment, a new stack frame gets created. So here's our stack growing this way, right? This is our stack. And the frame that gets created for the function increment has, among other things on it, the input parameters, the copy of the value. So the thing that we call value, so down here on the stack we have x, which we know is 4. So that's down here. But when we call into increment, a new stack frame is created, and a copy of that value 4 is put there. And so when we then update value, all we're doing is changing this to 5. When we return from that frame, from that increment routine, that stack frame is deallocated automatically, or what we call automatic memory. And you can see that nothing has happened to x. Right? So to understand how to make a function that can change the value of something, we have to understand how to write such a function. And we write that with, and you can see this in fact right here. We could, for example, printf the value of this pointer. Let's go ahead and print the value of p of x2. And then the final value here. This is adder of x. This is adder of value. Comparing those two values, what are they going to be like? Adder of value versus adder of x, from what you know already. Yeah, is there an answer? No, that's just that person going like this. How are those values going to compare? What can you say about them? Which one's bigger? Someone says x. Why? Yeah, the stack's going to kind of grows the negative direction. It just grows towards smaller addresses. So let's see if that's true. Oh, I should line those up better. Address of X. So you can see here, address of X, blah, 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 80C. The address in that stack frame, which is growing to smaller addresses, is blah, 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 7EC. It's a smaller number. So when we update that value, it doesn't do anything for us. It just updates some random value. So of course what we have to do, and you understand this, but you'll forget it at some point. And you'll get confused when we're trying to use this to change a pointer to a something. So we'll talk about that later. So we just change this. We pass a pointer to something, and then we update it indirectly by dereferencing it. So we have to, if we want to change the value of something, we pass the address of it here. And of course, here you can see that we can't print that. We don't want to print the address of that anymore, though we could. And we're going to see that we have the same address there. So that has the address, and we can update that thing indirectly and kind of do the thing that we want to do. Now, of course, you wouldn't write a function to increment a variable. You would say x equals x plus 1 or x plus plus, but you get the point. So important thing, we'll do some more review later. Memory model. Where are things on the stack? Where are they in the heap when we get to the heap? And how functions are called. If you can get that in your head, you'll have a lot of success. So, any questions? I hear a lot of chatter, which is only mildly disturbing. So let's turn the chatter into questions. Any questions? No, just chatter, yes.
Did we think before we were told to compile in 32-bit for the CS function? We have to do that?
No, I don't think for this project you need to. I think, but we'll specify those things. Some parts of the XV6 projects will be like that, but most of them won't be. Other questions? Yeah.
Can you talk a little bit more about the referencing?
Sure. So, I guess the way to think about this, and we don't have that much time, I just want to talk about a couple more things, is we want to be, people when were creating the C language, right, wanted very easy ways to manipulate things powerfully. So they wanted a little typing to do a lot. So it's amazing how much mileage you get out of this little asterisk, right? So what an asterisk in front of what value is doing, it's saying, well, it's of course assuming that value is a pointer. So that's an operator on a pointer. And if you think about it, let's look here for a second. If you think about our address space, there's something like let's say we have an int star p, and we have int x. So somewhere on our stack we have p and x, things that we refer to as p and x. Now the computer just refers them by addresses, and these addresses might be, let's say the address for this is 1,000, and let's say this one's 1,008 or something like that. Now, in reality, they're much bigger numbers. We saw those addresses are huge, right? It's a 64-bit address. But let's say there are 1,000 and 1,008. So when we say, for example, x equals 3, the computer is eventually going to turn that into, a store instruction of some type, which puts the value 3 into address 1,008, right? And that's how 3 ends up over here, right? That's how that works at a machine level. When we say p equals the address, that's an ampersand in my writing, not a 3. I don't know how to do that curly Q ampersand, my apologies. So this is an ampersand. So when we say p equals the address of x, I can try to do that ampersand. It's so complicated though. Sheesh. What is going on? The computer detected that I was going to fail, and it's like, I will assist you. Okay. I don't know what happened there. That was my first and last attempt to draw an ampersand. Oh, it's this cool thing actually. If you do like shapes, and you hold it, it's like boom, box. Yeah, that's computers. Okay. So anyway, p equals ampersand x. This is an ampersand. ampersand. What that's going to do is inside of P, it's going to put the address of X, 1008. That's what's getting put in there. When I say P equals address of X, it's putting 1008 into the container we call P. If I say P equals something else, like 0, well, it's just going to update this and make it 0. So let's get rid of that. Let's go back to 1008. Sorry, I lost the box there. Let's get rid of this. 1008. P equals the address of X. When we refer to star P, let's say we say star P equals 4. If we said P equals 4, it would just update this box. It would say P equals 4. But when we say star P equals 4, what we're saying is take this thing inside of P and then store to that address the value 4. So then what this is eventually translating is store 4 into the address 1008. And the address of 1008 happens to be, of course, the address of X. So when we do this star P equals 4, we're just changing this to 4. So it's an indirect reference. It is so critical to understand. It sounds really simple. We'll do more complex examples as we go. It's very critical to understand that. So let's just look at a couple more code examples for this project, and then we'll be done. Let's say we're writing kv.c. Hold on. Move kv. You don't want my solution already, do you? Kv secrets.c. Sorry, can't see my solution. So you want to think of this program in a couple of ways. Probably a few things. Like the first thing you're probably going to do is load the database. Loading the database means you are going to, however you store your database, load it into memory, like into a data structure, like a linked list. Then what you're going to do is for each command on the command line arguments, process them. So you can think of that like this. Something like, or let's start at 1, argc, And, for example here, we could just like print them out. Let's do that first. argvi, right? Something like this. And what we're going to do for each of these commands is process them. For example, a put or a get command. We might have multiple commands on the command line, like put this, get that, whatever. Then when you're all done with that, you're going to store the database. So that's kind of your basic structure. Now inside of this loop, and let's just run this program. This isn't too exciting because there's no commands, but we might have, put 10 Ramsey. This is apparently the only key value pair I can think of. And you can see here we have that command, and then we might say get 10. Now, we're not going to print these, we're just printing them out so we can see that we're processing it. We're going to start working on this program, so we're looking at it. So, what you're going to do inside of this loop, right? Very basic structure of this program is how I would think about it. Is first we have to parse each command and see if it's, and then if it's a valid command, do something, right? Whatever that is. Like if it's a put, do a put. If it's a get, it's a get. And so if you look at the assignment, what you can see is there's some suggestions there for parsing. For example, using the string separator to parse. So how do we learn about that? Well, we use our old friend. You could use Google, of course, but that's like such a amateur thing to do. You should just go straight to the man page. Manual pages. You can see here what we do here is we include string.h at the top. So let's go ahead and do that first. Fantastic. Now we can go ahead and let's look at how to use this thing. Usually these man pages have like a little example. So let's look at that example. In fact, I'll just copy it right here. And that kind of copying is okay, by the way. I don't like that too free. Let's call it that. Let's make a duplicate of the thing we want to parse, which is argvi. Assert the string is null. That's going to complain because I don't have assert in here. And then let's do this. That sounds fantastic. Well, it's already splitting it by commas, which is perfect, and then it frees it. And then let's do that. And do I leave any commas? No. Okay. So what it's telling us to use the string separator is going to look through there and help us parse out the pieces between the commas. So we have this commas between like put, comma 10, comma Ramsey, or get, comma 10. The string separator is going to help us with that. Of course, there's 1,000 ways you could do this. In fact, you could write your own string separator. You just write something that looks through each character and finds a comma, and then the first part is whatever. But this is going to be better than that because it's going to say, oh, here's a token, and a piece of that is whatever we're doing. So let's see if that worked. Oh, free? No, we didn't do that. So we have to, of course, look at malloc and free and know that we have to include standard lib. So let's go ahead and do that. Let's put that here. Oh, sorry. And then let's go ahead and compile it, and then let's do this again. And what you're going to see here is already we built a little thing that parses this and splits it out to each piece, P, 10, and Ramsey, and or get and G and 10. So now we have to do a little bit more work there because what you can see in this loop here is we're going to have to figure out that you have to figure out, is this a valid command or not, right? So as you're parsing each one, you have to keep track of a little bit of state and figure that out. I'm going to leave that to you. I wanted to look at one other piece, but we're a little bit out of time, so I'm going to just spend one more second on that. Let's say we want to load a database in, okay? Let's just look at that. For that, the project suggests you might look at something like fread and fopen and so forth. So let's go ahead and look at that. Any questions about that, by the way? Kind of makes sense? Okay, really quickly. Let's look at fopen. Fopen's pretty easy to do. We might say something like this. We might assert that fp doesn't equal null. And then what we want to do is use getLine or something like that. And you can see here's an example, again, in the man page, which you are 100% allowed to copy, about how you might read a database in. And we can talk about this line in a second, but let's go ahead and do this. So if we have a database like this, okay? Boy, there's a lot of chatter. Yeah, you can see like this. So you can already see the basics of how this thing is going to develop. And sorry, it's getting a little loud in here. I appreciate that it's more fun to talk to people. But let's just respect our neighbors who don't want to talk to you. Apologies. And you can see already we have like a shell of a program here. It's going to read in a database. It's of course going to have to put it into a data structure. It's then going to parse each command. And then it's going to execute the ones that are valid. And at the end, it's going to store it back into, say, that same file, something like that. And then already you have a working program. It won't take you that long. It should be like 100 lines, 150 lines of code, something like that at most. So that's a very basic introduction. Use Piazza for questions. We're going to, of course, TAs and peer mentors are going to help you. We're going to schedule lots of hours. Something to look forward to. Goodbye.